Hey guys, welcome back. We're going to go through the free response questions. Good times. So at the bakery where you work, the loaves are supposed to weigh 1 pound. So they're supposed to weigh 1 pound. And from your experience, you believe that they have a normal distribution with a standard deviation of 0.13. Wow, that's the population standard deviation. We never, ever get that. That's a big, huge deal right there. That's a game changer. Okay, let's keep reading. You believe that new personnel produce loaves that are heavier. So your sneaky suspicion is they are heavier. I picked that because they said the word heavier. Okay, so I must identify the population parameter in state. So I stated that, and then you have to define what that is, where mu is the true mean weight of loaves at the bakery. Now, some students are trying to figure out, well, which piece is what? Technically, that's a full answer right there. Beautiful. What are they saying the population? Well, the population are all the loaves at the bakery. That's the population. You don't have to write this for a full answer, but this will help you understand what they're asking you to write. And what is the parameter? That's the parameter mu, the true mean. That true mean is what we call the parameter. Okay. Now, we stated the null and the alternate hypothesis. Beautiful. Now let's get to identify the statistical procedure. So this is to remind you, you will say, I will perform A1 sample t-test for mu, but I'm going to say z-test for mu. Curveball, people. Normally, we have to say a t-test for mu, but we got to say a z-test for mu. Wowzers, that's a big deal. That doesn't happen very often. Okay, now let's do our conditions. So random, this we should write that it needs to be a random sample. 10%. Population is greater than 10 times the sample size, so the sample size is 20. Population, I'm hoping this bakery makes more than 200 loaves. Population is greater than 10 times the sample size, Okay. Normal, is this thing normal? Okay. Well, n is not greater than 30. So n is not greater than or equal to 30, but they said it's normal. So that's even better. They already said it's normally distributed. Okay, so those are checked off. Now let's calculate the t-test statistic. So normally you do t is x bar minus mu, or mu naught, over s sub x over the square root of n. So what do you do when it's z? Well, we can actually do a z because we don't have to use t to approximate z. So we still have x bar minus mu naught, but now we have sigma over the square root of n. So let's plug in these values from the calculator. Okay, so I get a calculator, I go to stats, and I'm going to do a z-test. It's rare, but every once in a while it happens. A z-test. And they gave me the summary statistics, not all the raw data. So I'm going to sort to summary statistics and hit OK. Now my mu naught, I'm supposed to assume that the loaves weigh 1 pound. And what is sigma? Well, the population per standard deviation varies by 0.13. What is x bar? That's our sample weight. So we see in the problem our sample weight is 1.05. So we do have evidence that it's a little bit heavier, but is that just pure variability? we're going to calculate the probability that it is pure variability. So we have 20 lows to work with, and our sneaky suspicion is it's something greater than that. We think of the word heavier. Okay, enter. Awesome sauce. I got a lot of good stuff in here. And again, remember we did a z-test. So let's take a look. X bar was 1.05, mu was 1. Sigma was given to us in the problem, and we took the square root of n, which was 20. So when the calculator adds all this together, it's right here, 1.72, 1.72. So what does that mean? Well, it wasn't 1, it wasn't 2, it was somewhere between 1 and 2 standard deviations from the mean, 1.72. So what is the calculated probability? How does it calculate the probability of that happening if it really is 1, but this was the outcome purely by chance? The likelihood of that is the p-value or the area under that curve. Now you can calculate it with table A, because this is z, or you already have it in your calculator. So they calculated the p-value here is 0.04. Great job, guys. Now, calculate the test statistic and the p-value and illustrate it. Done, done, done. Moving on. State the conclusion. Okay, so that's just our poster. Since the p-value, which is 0.04, is less than 0.05, we reject the null hypothesis. We do have sufficient evidence to conclude our H sub A. Now, we should say what the H sub A. What is the H sub A? That the loaves, again, you may have to look back up here. What was H sub A again? Oops, I forgot to put that there. What is H sub A? That the loaves, that the true mean weight of the loaves at the bakery are something greater than 1, right? That's what H sub A is. That the loaves are greater than 1 pound in weight at this bakery. Not at other bakeries, but at this bakery. Cool. All right, let's keep going. How we use the same thing but get a different badge. Let's see what's different here. Leroy starts playing, and it looks like he's got shot ratio. So we need to do a 1 proportion z-test. Let's take the information given. P naught. We're supposed to presume he made, actually, you know what? I already wrote this one out, but I'll do it anyway. We're supposed to presume that he has a shot ratio of 40%, but he's been working on his stuff over the summer. So he has a sneaky suspicion that he's better than that. We must define what that is. So where P is equal to the true proportion of free throws Leroy can make. Okay, so we've stated. Now let's get to our plan. So what is my plan? Well, the calculator helped me pick. I will perform a 1 sample z-test for B. Rolls right off the tongue. And I'm going to do my conditions. So random. You're telling Leroy, this needs to be a random sample, 10%. Your population needs to be greater than 10 times my sample, so it looks like he threw a total of 40, so 400. Population is as least as large as 10 times the sample. Normal. How will I test for normal, also known as large counts, when I ask a yes or no question? Okay, so I'm hoping we show some growth here. I take n times p naught, so I get 40 times 0.40, I get 16. And then I take n times 1 minus p naught, or 40 times 0.60, and I get 24. So we're good there. Both numbers are greater than or equal to 10. So all three conditions have been met, and I have stated my test. Now let's get to the do. So Z is equal to your test minus your predicted over your standard deviation. All right, so this is my standard deviation, right? So what does my calculator? It does everything, and it also helps me summarize that. So my P naught is 0.4, and he got 25 out of 43 for rows n, and we believe it's the proportion's greater than 0.40. Okay, so let's hit enter, and I get my Z, my P hat, and everything. Okay, so what is P hat? P hat's merely his sample. So he made 25 out of 40. So that's what the P hat is. It's this ratio, this decimal, 625. Now, what are we supposed to think? We are supposed to think it's only 40%. And so we use that number in the denominator, 0.4 times 0.6 all over. We took 40 shots. So what would this calculation come to? This, 2.90. Okay. So in this chapter, we have to make a picture, and I'm not 1, not 2, but almost 3 standard deviations from the mean. So to draw a picture, it would look something like this. My Z value is 2.90, and my P value is, what is the area under that curve? Well, I can tell you it's not a lot. My calculator tells me it's 0.002. 0.002. So I'm done with my do, and I can conclude, right? Since p-value is less than 0.05, we reject the null hypothesis. Right? We do have sufficient evidence to conclude H sub A. We must say what H sub A is to conclude that the proportion of his shots is greater than 0.40. That Leroy's free throw proportion is greater than 0.40. Great. Now for the last little part. It says construct and interpret a 90% confidence interval. So that's similar to a alpha 0.10 stat test. We already know that this is also less than that, but that's essentially what we're doing. But let's see it in a different way. So we go to confidence interval, and we're going to do a 1 proportion Z interval. Okay. So still the 25 out of 40, but my confidence level, I'm going to do 0.90. Hit enter. Okay, so how do we say this? We are 90% confident that the interval from captures the true proportion of Leroy's free throws. Okay, now what is my from here to here? 0.50 to 0.75. Wow, so that's awesome. That's awesome because, and we already knew we were going to reject the null because, so it says construct it and now interpret it. So I constructed it, right? And now I'm going to interpret it because our 90% confidence interval does not contain our null hypothesis. Once again, in this same way, we reject the null at alpha 0.10. It's the same thing as rejecting it. We do have sufficient evidence to conclude our, once again, it's the similar conclusion here. We do have sufficient evidence that Leroy's free throw proportion is greater than 0.40 because 40 did not fit and all the numbers that did create this were greater than that. Thanks so much for joining us. Good luck, folks.